to move around these huge video files to get people access. So, okay, looks like you guys are recording.
Can everybody see the screen?
Yep, we can see the screen.
Black box.
There's, yeah, the box.
It should go away in a second.
Yep, there you go.
All right.
Okay.
Now we just wait on the, so we are blessed with Cummins. Do we have Northrop with us?
Yeah, Sean Franklin with Northrop.
Oh, thank you for coming to our presentation, sir.
Glad to.
Joel Lucchetti also from Northrop.
Thank you.
I guess the question is, Dr. Trump, is everyone that needs to be here, and may we start?
Oh yeah, go ahead. Sorry, I thought you guys had already started. Go ahead.
Oh,
okay.
no, sir. Sorry. All right. All right.
Okay, Kelly, go ahead.
Well, hello everyone and welcome. To address the need for a lift and dynamic body weight offset system that aids in rehabilitative exercise, our team presents Gatorade. Next slide, please. With our proposed design, the participant is lifted from their wheelchair through a motorized pulley and harness system. The participant is then guided to the elliptical machine by a rolling frame. The magnitude of the desired weight offset is set through the force of tension in the primary support cable. To maintain a constant weight offset while the participant is translating up and down, the central weight offset assembly also translates vertically. This compensation is accomplished through a motorized dual lead screw system that takes feedback from a tension sensing load cell that is on the primary cable. During exercise, the user interfaces with the system through a tablet that is mounted on the face of the elliptical. To protect the participant in the event of a system failure, or if they experience any feelings of discomfort during their exercise, our design includes a backup cable, as well as multiple emergency stop buttons and switches. Next slide, please. Our design is divided into 5 subsystems, which are lift and harness, weight offset, power supply and distribution, safety, and user interface, which our team will now expand upon. And in the coming slides, you will see that on the right-hand side, as in this one, we have presented our customer needs that we sought to address in each of our subsystems. Next slide, please.
With regards to the lift and harness system, we decided to make we aim to make the frame as light as possible and also mobile. So with that, the entire frame is designed with aluminum 6061, which resulted in a net weight of 76.3 kilograms. In addition, the entire overall footprint is 1 by 2.5 by 2.7 meters. This allows the tallest participant to be in the machine to be 2.03 meters. Lastly, the entire frame itself is designed to accommodate not only the elliptical, but also other machines such as a treadmill itself. With regards to mobility, we decided to go with 4 2.5-inch leveling casters that each had their own bubble levels on each foot to accommodate for leveling the actual platform. With regards to the lift system, the participant is attached to the actual frame through a Kevlar rope. The Kevlar rope is fed through a pulley system that goes through the cantilevered beam and ultimately attaches to the main mobile frame. With the assumption that the entire device will be pushed at a rate of 0.25 meters per second, the max swing that the participant will experience would be 6.1 centimeters. With that, the idea is that the participant is going to be lifted out of the wheelchair through the harness, and the entire assembly will be pushed a total of 1.14 meters until the participant is on top of the assembly and placed within the boots to start their exercise or their actual therapy session. Next slide.
So in order to ensure the operation remains well throughout the entire device, we ran finite element analysis on our cantilever beam. We assumed a maximum loading condition of 350 pounds, which is our maximum weight we expect a patient to be. The boundary conditions were that the beam, the top bar itself is fixed, and then it is bolted in, the cantilever beam is bolted into that top bar with a contact set between that top bar and the cantilever beam. The load is applied on the pulley connections at the end of the cantilever beam, and with those conditions, a max stress was found as 57.2 megapascals, which led to a safety factor given our aluminum 6061 frame as 4.49. The max deflection was 1.35 meters, and we also ran a fatigue study to ensure that it would withstand our 6 million cycle optimal life. and that was determined to be 33 million cycles, where it would ultimately fail at that stress concentration at the flange. Next slide, please. We also ran a tipping analysis to ensure the device would not tip during operation. So the max participant weight before tip was quantified with under two conditions, a swing and no swing. Under swing, the max participant weight could be 280 kilograms to the point, at that point, the weight offset or the weight would be too high and the frame would tip, but 280 kilograms is far above what our operable weight is. And then with no swing, it is 303 kilograms. These measurements are based on the average participant center of mass, which does change from human to human as body proportions change. But the key takeaway from all of this is that the system will not tip if the center of mass remains behind those front caster wheels. Next slide.
For the power supply and distribution, we used the customer needs specified. We had to plug into the wall and maintain the 15 amp max current. And we wanted to make sure that we got the emergency cutoff. The user and trainer are available to ensure that happens. And then we also need to be able to automatically cut it off based on a force limit. And to do that, we used a 48 volt power supply. And it is frame mounted to maintain system mobility. So it's mounted to the side, and then it's also plugged into the wall to maintain that 120 volts AC. That drives two individual stepper drivers, which drive their own motors on the side, which you saw in the first slide, I believe. And then the control system is fed through a Arduino Nano, and it is covered by a cover, which you'll see later, and then mounted next to the user interface so that it was easy to get to. The design features have putting the Arduino right next to it, so we limit the cables that are hanging and might get caught up in the activities. And cabling is dressed along the frame so that there is very little impact on the transition around and through the frame. So for the weight offset, we chose to go with the aforementioned NEMA 34s. There are one in the middle, and then there's one on each side. The one in the middle is basically static. It lifts up the person to hold them in position. I think they went over that a little bit. And then the ones on the sides control our dynamically adjusted weight offset. Our control system is fairly simple. It looks for a target tension, and then it feeds it back through a PID loop and just keeps chasing that so that we can see the force through a load cell, which has a max capacity of 440 pounds. So it achieves the max participant weight that we would see. For the weight offset, the middle motor translates up and down with the middle traverse, and the lead screws on the side individually would move that up and down. So the ones on the side are just slightly different, but they are they do have encoders on them to ensure that both of them move at the same rate and the same distance. So that's all fed through the control system, and the factors of safety are still taken into account. And the operational lifetime is 3 times greater than the standard elliptical. So we made sure that we adhered to that.
So moving on to how we chose those motors and why, and meeting the criteria that we had set in place. So like it was previously mentioned, the heaviest participant that we're expecting is 350 pounds per customer needs. And from a motion study, we basically determined that a vertical translation of 2 inches per second to match the participant would be enough. So in order to basically achieve those 2 requirements, for the side motors that do the dynamic weight offset, like Daniel said, we went with a NEMA 34, like he mentioned, and that will be roughly running at 600 RPM. And with a combination of a 3H 4-start lead screw, we can get up to 5 inches per second of vertical translation, which should be more than enough for the standard participant that's like we studied going at 2 inches per second. Now for the middle motor, which is lifting the participant up out of the wheelchair into the vertical upright position, it was determined that the max load or torque would be 39.5, and that motor is running at a much lower RPM and is able to keep that high torque at the lower RPMs like stepper motors usually tend to do. And for both of those motors, we were able to achieve the design factor above 1 for the heaviest participants. Next slide. Sorry. That entire drivetrain attaches to a motor mount. That motor mount is both seeing the load of the patient and the load of the motors. So the design was basically, so the FEA was running ANSYS, and the boundary conditions were attaching this mount to the transverse beam with cylindrical supports. No preload was applied because there was no concern of crushing this part as it is solid. There's 2 loads applied as remote force to essentially apply a moment on this part. One was the weight of the motor with the gearbox, and that was roughly 15 pounds. And the other side, of course, the moment that the person is applying through the rope. Through those boundary conditions at 350 pounds, we saw the max stress concentration at the mounting holes was roughly 117 megapascals, which gives us a factor safety of about 2. Next slide.
This is our interface subsystem. Consists of a Microsoft tablet as well as a 3D printed mount, which can be seen in the figure on the bottom right. We selected our tablet based on the fact that it had to be compatible with the software that is often used within the NCR lab by our customer, as well as the multiple customer needs seen on the right. This software includes Simulink, LabVIEW, and other control software. This device also has a high refresh rate and a programmable interface, making it optimal for use by either a user or a clinician. Standard features that come with this tablet that also made it ideal for our situation include an on-off function, mode functioning, and the ability to program into it a weight offset amount that could be adjusted on the fly. Next slide.
With regard to safety features, we have the listed safety features in tabular format. Starting with the emergency stops, we have a total of 3 emergency stops on this design. The first 2 are located on the sides of the frame legs for actuation by the trainer or assistant in the event that unsafe operation is detected. We also have an emergency stop under the user interface mount, or such that the participant can actuate it in the event that they feel unsafe. Additionally, on top of the user interface mount, we have an attachment for a recessed reed switch, which is normally closed when the participant is exercising, but in the event of a fall, the reed switch is opened and operation can cease. Additionally, we have a backup safety rope that is attached via an eye bolt to the cantilever beam. And this is simply to catch the participant in the event of a fall, a loss of tension in the spool, or a breakage in the main lifting cable. Furthermore, a tension sensor that was previously mentioned is attached via the harnessing rope to the participant's harness in order to let us know if the force limit is exceeded. Furthermore, in the event of a motor failure, we have mechanical stops in the C-channel legs to prevent the beam from transversing past the allowable limits where it could damage either the NEMA stepper or the encoder. Next slide, please. So here we can show you the actual locations of each of these parts. We see that the e-stops are on either side of the leg such that the installation can be actuated from either side. We also have the e-stop directly under the user interface so that the participant has it well within reach of handles in the event that something goes wrong. We can see on the middle image that we have the eye bolt mounted as close to the main lifting cable as possible to prevent any horizontal component of force in the event that the patient falls, so it doesn't pull them back too far. And slightly to the right of the backup cable, we can see the small force transducer attached to the carabiner at the end of the gray cable. The mechanical stops take the form of shoulder bolts that will prevent the middle transverse from exceeding limits. And finally, you can see in the bottom right that the reed switch is recessed into a 3D printed mount. In the event that the participant falls, the key, which is attached via a cord to the waist of the participant, is pulled out of the read switch, sending a signal to the Arduino, which is mounted to the left of the user interface, to cease any operation of the machine. Next slide, please. With regards to cost estimates, our main focus was to meet the cost limit set by the customer at $4,000 for consumer off-the-shelf parts, material cost, and shipping and handling. With regards to consumer off-the-shelf or commercial off-the-shelf parts and material costs, these were sourced via a variety of suppliers, chief among which were McMaster Carr and Metric Metals. And we calculated these costs based on surplus cost considerations, such as fasteners, where we purchased based on the used amount of parts. When it comes to shipping and handling, that was calculated with regard to the full order, and that was obtained via quotes from the supplier. So this is, of course, subject to change in the event that we are producing more than one unit, because they did mention to me that they could supply bulk discounts. So for the total on the top side, which is the cost for a prototype, we have $3,895.43, which is under the $4,000 cost limit. Finally, we have also done some very high-level manufacturing, energy, and assembly calculations based on some manufacturing time estimates, energy estimates, and Boothroyd and Dewhurst insertion times to give us a total cost for production of $3,979.20. Proceed.
So to summarize our presentation and to begin our conclusion, our key features include our lightweight and mobile aluminum 6061 frame. As you can see in the figure on the right, we can package it in a very small box to send and ship in a very quick fashion. Another key feature is also our dynamic weight offset system, where we use 3 stepper motors, one that provides continuous load and 2 that move synchronously to adjust for offset parameters that are predetermined. We also have a device that has a large variety of exercise machines that it could be compatible with, and an adaptable and programmable user interface method. Next slide. I'd like to end our presentation by thanking all of our instructors this semester and our sponsors, the Department of Mechanical and Aerospace Engineering, NCR, Cummins, and Northrop Grumman. And we'd like to open the floor up to any questions.
Okay, questions from the panel.
Hey guys, great job on taking so many things into consideration as far as the safety and user interface. And I just had a quick question, you know, as the user of this system, the one thing that I'm interested in is how fast can my elliptical go? Meaning, like, you gave a speed of 5 inches per second, but like what RPM does that relate to for my elliptical? And kind of what amount of offset are you accommodating for?
So from the motion study testing that we did, we didn't get a value for the elliptical cyclic time, you could call. So it was more of like the normal participant that we're expecting should go at this rate of speed. So that's kind of what we based off of our vertical translation. So we didn't really get a number. It was just from the physical observations that we saw that we would expect the participant to be at. In regards to the offset, do you mind further clarifying that? I didn't really understand what you're referring to.
Oh, I'm just asking that, you know, given the expected RPM of use, you know, how much offset are you expecting to be able to get? But it sounds like you don't have an expected RPM, how fast I can operate my system, and then at that speed, like how much offset can I accomplish, if that makes sense.
Right, yeah, so at few different speeds, we kind of saw the same vertical translation. So ultimately what we cared about was satisfying that need of a vertical translation, not so much the machine RPM, because ultimately that's what it translates to, the vertical translation, which we're trying to synchronously dynamically offset. That makes sense.
Okay, so just something to consider moving forward to your FDR is that the RPM does actually affect the inches per second velocity, because the faster I'm rotating at, the more quickly the system has to accommodate, and the faster, excuse me, that translation needs to take place. Just one other real quick thought. There were 2 slides. I can't remember exactly where they were, but one was giving the weight that you were offsetting in pound feet, and then the very next slide went to kilograms. You were giving, how many kilograms the system could carry. And I would just recommend kind of trying to keep everything in the same units because it's easier to kind of track the presentation that way.
Thank you.
Yep.
Yeah, Kim, I noticed that too. That was on a couple slides. There was some changes from metric to standard. But yeah, it was. But overall, nonetheless, there was. I think you guys did a great job. Looks really good. You guys definitely took the time to put in a lot of detail. And I think with the $20 that you're saving, you guys could add maybe some lids to those pinching to the lifting mechanism. I noticed there was the screw there, right, as it's lifting. That'd be something extra to add there. But I think you guys did a great job. You guys look. I appreciated the package in the box as well. That was a nice touch. Looked really good. So good job, guys.
Thank you.
Thank you very much.
To speak on that, a lot of our design was keeping in mind the end product and being able to package, ship, and assemble pretty easily with a minimal amount of people. And we carried that through the whole design to try to emphasize that. So we were trying to help the people that were going to set it up in the first place, or if it does go into mass production, when it goes into mass production. Then it would be easy to implement into various amount of environments.
Hey guys, great job on the presentation. I liked how you showed the free body diagrams and the analysis that you ran and really explained what the loads were. I was wondering if you did any bolted joint analysis or shock load analysis for if someone suddenly drops.
Yeah, so we did take into account the impulse load of somebody dropping. Just keep in mind that with the given control system that we have, we should always have a tension on the rope. So that's why it really wasn't taken into account for the motors or the motor mounts, but that is not the case. If that rope were to break, the secondary rope would take that impulse load and the cantilever beam over the top of the patient would see that load. So we did take it into account. David did the analysis for that. He can probably talk more in depth regarding specifically what he did.
Absolutely. So we estimated an impulse load about 2,400 newtons with a fall time of 0.15 seconds. That led to a stress, same concentration of the cantilever beam in the same point at that flange. The max stress with that impulse load was 97.2 megapascals, which led to a safety factor of right around 2.5, about 2.46. And our cutoff safety factor was 2, so we still felt comfortable with the design given that impulse loading.
Thanks. Also, I was just wondering, other teams seem to use this winch design. What made you go with the motors?
Yeah, so the stepper motors, those specific ones, when choosing what type of motor to go with, stepper motors tend to keep their torque curve pretty high at low RPM, which is the case for us. The middle winch motor has a 10-to-1 gear reduction, so we are able to get the torque at the speed that we're running at. So that's essentially what made us pick those specific ones. That answers that question.
I would also like to add, in addition to that, with regards to our motor selection, we also were at the beginning planning to implement a commercial off-the-shelf winch. However, from research, it seemed like most of them drew more power than what we needed with regards to the customer needs power supply. So that also limited our choices of winches. So we decided to go with also the NEMA stepper motors instead.
Thanks.
Hey, thank you very much for your use of animations at the very beginning. It really showed us how the system was going to be used and gave us a sense of what the interference was between the elliptical and the machine. Thanks.
Thank you.
I was going to second that. I think that was a really good touch. Guys did a really good job on the presentation. I did have a quick question about the tipping calculation. If you can go back to that slide real quick.
Yes, sir.
And I guess my question was this assuming the max weight of 350-pound user, or how did you come up with these weights?
David, would you like me to speak on it, or?
Yeah, Roberto, I think you would be best to speak on it.
Yeah, so the center of mass calculations were taken into account with a 350-pound user, so since that is the heaviest participant that we're to expect. Like David mentioned, it is kind of difficult to determine where that is going to be, because everybody has a different body proportion, so your center of mass is going to be slightly different. So we just took an average of the standard participant that we would expect, and
Standard height, you mean?
Yeah, exactly.
Oh,
yeah.
Okay.
And we're able to determine that essentially it's some of the moments around a common point, which our origin was right in the intersection of the feet and the legs. And yeah, some of the moments making sure that that moment is above 0, which would mean that it wouldn't tip over at the given center of mass location.
Okay, thanks. Good job.
Thank you.
Okay, so we'll have to stop there because we're running over time. Just for the panelists, if there's anybody joining us new, I've just sent to the whole group in the chat the URL of the landing page for the event. So the next group will be starting at 11:30, which is effectively now. But to get that Zoom link, if you head to the landing page, you can find the Zoom link for 11:30. So we'll reconvene there in just a moment. But want to thank this was Group 8, right? The dream team.
Yes, sir.
Yes, sir. Yes, sir.
So I just want to thank you guys for sharing your design with us. And I have to also echo how cool I think those videos are. So I know you guys put a lot of time into figuring out how to make those look good and run smooth, and it really adds to the presentation. So I appreciate that you guys did that.
Thank you, sir.
So, all right. Thank you. And panelists will reconvene in the next meeting in just a few moments.
Thank you for joining us.
Thank you.
Thanks, guys.
Hey,
Thanks,
Daniel.
guys. Have a good one.
Thank
Hey,
you. You
Daniel.
too.
Thank you.
This is Warren. Sorry I had a conflict and wasn't able to watch you guys' presentation. I was able to watch every other presentation today except for you guys, and it looks like I missed a fantastic one. I know you guys have been working closely with Kim, and even the few slides that I saw here and the way you answered questions was good. I would really love to get your video, though, your recording of the Zoom. So
Yes, sir.
As soon as you guys, you'll get an email from Zoom, asking you to save it from the cloud and everything. But as soon as you guys get that and grab it from there, I'd love to see it so I can kind of get back up to speed.
Thank you, sir.
Will do.
Thanks, guys.
Thank you.
Bye, guys. See you later.
Thank you. Bye. All right.
Good job, guys.
Thank you.
Thank you.
Thank you.
Group 8, stay on.
Well,
Right.
I would say
Oh.
thank you.
Here.
We were planning to stay here, but since it is being recorded, we might want to. I don't know if you can stop the recording now or
Yeah,
end
you
the
can stop
meeting.
the recording
Okay.
without leaving. You might want to show Dr. Nimi your.
Is he here?
Yeah, he is.
All right.
Yeah,
One
but
second.